topic last time? Where did we end? Raycasting? Okay. All right. So what are we doing? So the first assignment, right? We are working our way towards the first assignment, namely an assignment where we will compare the typical raycasting, the way it's done, with trilinear interpolation, versus the raycasting that I ask you to do here in comparison, namely to use tricubic interpolation. Typically, the building block of any raycaster is you have the ray passing through a volume element, a voxel, right? You shoot the ray through that voxel, and along this ray, in that voxel, you have to sample and compute some function values, density values, and opacity values using some transfer functions, right? That's what you do. When you can do that, then you produce ultimately the color for the pixel. That's raycasting. Now, and the essential operation is to do the interpolation inside a volume element very well. Now, the typical way to do that, or the typical way it's done, is trilinear interpolation. You have a voxel, right? 8 corners, 8 values, 1 function, and that 1 function is trilinear interpolation, because all you need in graphics is linear, bilinear, trilinear, multilinear, right? That's all you need. But that's not good enough. Why isn't that good enough? Because when you render, when you create a volume-rendered image of a simple function, as simple as x squared plus y squared plus z squared, and you sample that on a nice Cartesian grid, you will not see beautifully spherical shapes at coarse resolutions. You will see a bunch of little concentric shells popping up, right? You can do that, and you will see that very easily. Why? That is a consequence of the trilinear interpolation not being good enough to give you something in terms of normals that leads to good color values and therefore to smooth images. Okay, so therefore, it's important to know that for certain applications, it might be good enough to just use something like linear, bilinear, trilinear. For the majority of applications, particular scientific applications, it is not good enough at all. You need much higher degrees to actually do scientifically correct or proper or more appropriate interpolation, approximation, visualization. So this is just one exercise that should open your mind to using higher order schemes for interpolation anyway, whenever you know that a particular phenomenon that you want to model or that you want to make a picture of is of a much higher complexity than you could possibly model or capture with a line, right, with a bilinear patch and so forth. All right, so what is the context? The context is raycasting. The goal is, I call it smoother, okay, smoother raycasting. Emphasis on smoother. What is the basic operation? What is the scenario? The scenario is, in the simplest case, we have a nice Cartesian grid of sampled data, and that's all I ask you to do for the first assignment anyway, dealing with the simplest of grids. A grid like that is also numbered with integers, x equals 0, x equals 1, x equals m, y equals 0, 1, 2, n. All right, and then I also ask you to merely produce raycast images onto an image plane, which is, well, parallel to one of the faces of the bounding box of the data set. Okay? So say this is your screen, which is nicely aligned with the orientation of your entire volume. And then the essential operation that you have to do for each of these pixels here, the viewer standing here, looking through this particular pixel, the essential operation for raycasting is shooting the ray through your grid and then accumulating the opacity and color values according to that formula that Mark Lavoie has written up in his paper. So here we have the ray going through there. Here we have some kind of light source, illumination, and then the critical part is related to sampling this ray in the interior of all the cells. And usually you want to make sure that you use a number of samples in a cell that allows you to have maybe 3, 4, 5 samples per cell. Again, that's a different topic, why that's important, that you relate the resolution of the sampling to the size of the cell. It's a different topic I'll talk about next time. So what do we need? What's the most important operation when you integrate or accumulate or sum up all the color values? The most important operation is, well, the computation of a color value at this location inside that voxel or grid cell. And, well, the most important element that governs computing the color on a surface, this is a contour surface that lies in there magically, well, is the normal to that surface. And the normal to the surface happens to be the gradient of the function defined over that cell. Okay. So the need to sample array R. So this is our happy array R inside each cell it passes through. And the most important thing is we need to compute very good high-quality colors, local colors at this location. Yeah. As I said, we need to compute a local color value, Ci, and the local opacity value, alpha I, right? And both of these values, Ci and alpha I, will depend on the way we interpolate the data over this little region in space. So necessary good values for these local color Ci and alpha I. Okay. And as a consequence of that, we need high-quality normal vectors, and the normal vectors are the gradients of the function we compute over that element. Okay, so this is our normal vector, n for normal. We need high-quality normal n estimates. That's the context. Okay, and all I'm talking about now is how to interpolate the function over one of these cells. Thus, need high quality or higher quality data interpolation schemes. Who has taken ECS 178? Who has come across the Bezier curves or Bezier surfaces in one of the courses before, graphics or visualization? You have seen some of those. Okay, that's good. So then you have to help me, right? I'm the old man, right, whose memory is failing, so I will make lots of mistakes, and you have to tell me when I make a mistake, right? So, okay, motivation. Motivation is just the 1D case, right? Oftentimes, it suffices just to understand everything in 1 dimensions, because then you can generalize to 2D, 3D, 4D, and so forth. Sometimes it is not enough. We will see later. Motivation, smooth interpolation of 1-dimensional, 1D, or univariate data. Okay. So, in this case, in the 1D case, what are we given? We are given some kind of x. And in the Cartesian case, we have sample values here. And if it's a Cartesian grid, then this location x0, x1, xi, and xn, these guys would be just integers, namely 0, 1, I, and n. And I have function values here. A first one, a second one, an ith one, and an nth one. And if linear interpolation was all that I needed, then this function is good enough. Okay? But this normal computation is related to, well, something more than just a function value. It's related to the curvature, the slope, the gradient of this thing. So do we want this? This is piecewise linear, right? Piecewise linear interpolation for some purposes it's good enough. In the context of volume rendering, it's not good enough because, well, the slope abruptly changes from being 1 to being -2. It's bad. And it will show up, okay? Jumps in there all over the place. At every breakpoint, there's a jump. So this is very bad and makes us sad. Okay, it's not good enough. So we want something better. Depends on the purpose, but for our purposes it is better. We use something that is called piecewise cubic interpolation. Where the same data is given, x naught, first one like this, ith one like that, last one like that. So this is again location 0, location 1, location I, location n. Cartesian grid, integer coordinates. And here are my data values. And I want to get something that is much smoother, namely something like this. Okay. So there, the slope, the tangent is the same, is continuous all along the curve. That's what we want. Nice. And we smile again, right? So the question then is, how do we generate this? We need to understand one building block, right? What is the building block? We need to understand one of these segments. This is the building block. Building block. Building block. And we only need to understand how it works for one of the segments, because the same recipe then can be applied to all the segments. Okay? All right, so let's do that. The building block. So without loss of generality, I can always just talk about the building block as being the first one between 0 and 1, which makes everything much simpler, okay? You can treat each of these cases as if it was the case from 0 to 1, 0 to 1, okay? If you so always assume that things are parameterized, defined over 0, 1, many things become simpler. And for the purpose of actually constructing the overall curve, it doesn't matter. It can always be from 0 to 1, okay? Can always assume that each, and these things are called the segments of the curve. Segment. This is a segment. That each cubic segment is defined over 0, 1. Can always assume that each segment is defined over the interval 0 to 1. So then we have the following case. We have an x. We have a first value. And we have 0 here, 1 here. In order to define a cubic segment over this stretch, are these two sticks sufficient? This is all that I need to define a cubic curve there, or do I need more or less? A linear piece requires 2 data, right? 2 points give a line. But a cubic curve requires how many data? 4? 2 points plus 2 slopes, 2 derivatives, for example. But it requires 4 bits of information, right? A line requires 2 bits of information. A cubic requires 4 bits of information. And so, well, if you want a cubic there, then, for example, you could define a cubic by having a first value. I call this guy f0, right, because it lives over 0. And I call this guy f1, f for function value. And then I also need, well, this would just be the line. but I want to prescribe the slopes. Maybe I want to have this slope here, and I call this G, G1, G already for gradient, okay? And I also specify a gradient or slope here, and I call this G0. What will the cubic curve look like that interpolates to these 4 pieces of information? Well, it will look like this, right? Something like that. Okay, so this is that cubic curve. Cubic defined by 4 pieces of info, namely F0, F1, G0, and G1. So this is one segment of the curve. And so this function f of x, if it's a cubic, is of the general form fx is some kind of a plus bx plus c x squared plus some d x cubed. But this is not the form that I like. This is not a Bezier curve. This is a standard monomial form, which is ugly, not nice. So that's why I will change that. Okay. But much better to use what is called the Bernstein-Bezier. Bernstein-Bezier basis. And an illustration how that looks like. And then I'll also tell you why this is better. At least in one sense better. It's better in many senses. So here's the first stick, here's the second stick. We call this 0, we call this 1. This is height number f0, this is height f1, 2 function values. And then a Bezier curve, and you remember that there are polygons for Bezier curves, and these polygons resemble the shape of the ultimate curve, right? That's why what makes them nice. If I give you a polygon called the Bezier control polygon or a curve control polygon, the curve that is implied by the polygon follows the polygon very closely. So if I give you now these additional Bezier points, these are Bezier points, circles, and then I wanted to have this a slope like this. This is a Bezier point, a slope like this. Here's a Bezier point, and this is a Bezier polygon. These 4 circles connected, and then this Bezier polygon implies a curve like that. That's why this representation of the curve using the 4 circle points is much nicer. What are these points called? They are called Bezier point, right? They are B for Bernstein-Bezier, B0, B1, B2, and B3. Okay, so the cubic defined in terms of the Bernstein-Bezier basis looks like this. It's the same function. It's the same function f of x. But it now takes on a different shape, form, representation. It has coefficients bi times polynomials bi3 of x, I from 0 to 3. Is there anything that doesn't make sense? in terms of the picture, so what I'm talking about? Is everything clear so far? It's okay? No questions? Okay. All right, so then let's see what this is. More. So what is this? So this function f of x is the sum I from 0 to 3 bi times bi3 of x. And I haven't told you what these polynomials are, right? These basis functions. In this case, the basis functions are very simple. The basis functions are x to the power of 0, x to the power of 1, x to the power of 2, and x to the power of 3. These capital B functions are different. And I have to tell you what they are, where these Bernstein functions, bi3 of x, are defined as 3 choose I times 1 minus x to the power of 3 minus I times x to the power of I. Okay, and we need specific ones. Specifically, we need the ones from I being 0 up to 3. So I just give them to you what they are. B03 of x equals B13 of x equals B23 of x equals, and B33 of x equals. Okay. Now, what is this 3 choose I thing? It's a binomial coefficient. You remember that guy? This guy is, I always forget, what is it? N choose I is, help me. I'm the one who has forgotten these things, not you. N choose I. You have to some combinatorics, right? And permutations, all of that. Yes. So it is this 3 factorial thing there, right? Divided by I factorial over 3 minus I factorial. Okay, that's the binomial coefficient, all right? So now you can just plug these different values in here and they get the different functions. There's always a pattern, right? So you'll have I go from 0 to 1 and do it, and you see 1, 3, 3, 3, 1, right? Okay, 1, 3, 3, 1. Times, and now you have the powers of 1 minus x, okay? 1 minus x, 1 minus x, 1 minus x, x, 1 minus x, 1 minus x, to the power of 3 divided by 0. Okay, so it starts with 3 and then it goes down, right? And then the other power of x goes up from 0 to 3, so it is times x, times x, times x, times x. And then it starts with 0 and then goes up. Okay. And now I can collect terms and simplify that. Okay, then I just see this is just 1 minus x cubed. This guy is 3 times 1 minus x squared times x. This guy is 3 times 1 minus x times x squared. And the last guy is just 1 times x cubed. So these are the guys that you will need for all your assignments, okay? I just give them to you because they are so important, so that's why I spelled them out for you, okay? All right. Where is all this going? Why is he talking about this stuff? Now we utilize this, right? Now we apply this. Now we apply this. Okay. We want to construct an overall curve that is smoother than a piecewise linear one. So therefore, we are just given this stuff, a bunch of sticks. That's all we have, but I said that doesn't suffice to define all the cubics. So what else do we need? In addition to the sticks, we need derivatives, right? Estimates. So where do they come from? They are not given to us, so therefore we compute them ourselves. Right? So what is a good derivative for this guy? Is this a good derivative for this guy? Is your eye seeing a slope like that at this point? What is your eye seeing? Your eye sees something different, right? Your eye is probably seeing more something like maybe that. Is it better? Maybe like that, maybe like that. Okay. Those could be good ones, right? Good slopes. And then you get a curve like that. That's not too bad, right? It's not too bad. It's okay. So from the sticks, we need to compute these little slopes, the tangents, okay? Thus, from given fi values to good slopes slash gradients, right? Slopes slash gradients, G gradients, gradient estimates, GI. Okay. So again, we only need to understand the building block, how to do this. Building block. Okay, so the building block is just concerned with 3 sticks. Right? And we want a good estimate for the stick in the middle. How do we get it? So this, say, is location I. This is location I plus 1. This is location, or location I minus 1. So then this has a certain length. This is the length of 1. This is the length of 1. This guy, these guys are the only ones that are given in this neighborhood, and they are called fi minus 1, fi, and fi plus 1. How do I get the slope there at the middle? What is a good slope? When my hand is, it is sloped properly, tell me stop. What is good? Stop? Okay. Stop is this is good, right? So you say this is good. Burn stop here. This is good. Okay? Yes, it is, because your eye sees there's something like this going through there, right? This is not the cubic. What I did there, I used 3 points to fit something there. And then I used this thing there that I fitted to get that guy, right? That's what your eye did, implicitly. So I just tell you that something that might describe the action of your eye was that your eye was fitting a little parabola through there. Okay. 3 points define a parabola. So this parabola looks like that, and this parabola would have a certain slope there. And the slope of the parabola is used as the gradient at location I, GI. Okay? So this is just GI. Okay. And so now I just give you the formula. The building block is step 1. You fit a parabola. Your eye is doing that. Fit parabola through these sticks, fi minus 1, fi plus 1. Okay, step 2. This is this happy parabola which I'm drawing. And when I differentiate the parabola, I get a good estimate for this location I. Differentiate this parabola. Differentiate parabola at location x equals I, and you get the derivative there, gi equals, and someone tell me what that is. You've seen it in graphics and visualization. This formula is again a universal formula. The gradient in the middle is it's always right minus left divided by 2. right? You've seen this formula many times in many papers. It's always 1/2 times value to the right minus value to the left. That's where all of that comes from. So the gradient is 1/2 times the value to the right, fi plus 1, minus the value to the left, fi minus 1. Okay? That's all you need to know for getting derivatives in computer graphics, right? That's just the formula you see there all over the place. Who has seen this formula before? It's always 1/2 times right minus left. Come on, you all have seen that, right? This is where it comes from. There's an implicit fit of a parabola. This thing is differentiated at the middle, and the assumption is that the spacing is 1 unit. Okay? If these assumptions no longer apply, then the formula becomes much more complicated. Okay? So all these papers that you see, where you only see this very simple formula, assume that everything is on a nice Cartesian grid. In the real world, nothing is really assembled on a nice Cartesian grid. So whenever you apply these simple formulas with 1/2 times something, right minus left, blah, 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 and you apply it to a non-Cartesian setting, everything is wrong, right? So anyway. All right. So far, so good. Now we need to know how we get our cubic Bernstein function for that. Now we can construct a cubic polynomial segment in Bernstein-Bezier form. All right, what is the setting? The setting is we have an x. And again, we have many, many sticks lying along this line. It doesn't matter which particular neighborhood we look at, it's always the same. We apply the same scheme over and over again to the same setting. So therefore, you can also trivially parallelize the whole thing, right? If you have multiple processors, the many different processors can solve the thing locally. So I only care about this setting. I have 2 sticks. And again, without taking away from generality, I can always say 2 sticks always live above 1 and above 0. I have 2 values there. And at this point, I have also these guys, right? I also have the gradient estimates at this point. So I have an f0, an f1, and I have the slopes, which are called gradients, gradient 0 or slope 0, and I have another one, gradient 1 or slope 1. But for the Bernstein-Bezier representation, I need these b points. I need these coefficients small b. Those are the coefficients, right? And I tell you that these coefficients have this beautiful geometrical interpretation. The first coefficient is this guy. The next one is this guy. The last coefficient is this one. And the second to last is this guy. Okay, and so now I can connect these circle coefficients with this polygon and the resulting curve. This is nice, beautiful, happy little cubic curve that looks like that. Okay, so the circle point there is circle point B0. This would be B1. This guy is B2, and this one is B3, right? But I need to tell you how the B0, B1, B2, B3 values are related to the given stuff that we have now. At this point, what is given? Given is F0, F1, and G0, G1. And those 4 pieces of information imply the B coefficients, okay? Given the F0, F1, G0, G1 values, the values for the BI coefficients What is obvious? B0 equals, the way I've drawn it, F0, right? B3 equals F1, but these guys in the middle are a little bit more complicated, right? So I give them to you and tell you how they are derived. B0 equals F0, B1 equals F0 plus 1/3 times gradient 0. B2 equals F1 minus 1/3 G0, and B3 equals F1, and that's it. And this is really all you need also for the volume case, but the volume case is just a generalization of that.
Should that be G1 for B2?
Very good. G1, 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 G1. Okay. Where does the 1/3 come from? The 1/3 is related to the fact that this thing is of length 1, that these distances are 1/3, and that you are going in this direction at the slope of G0, and here you go backwards minus with the slope of G1. Okay, that's where that comes from. That's the way you can think of it. So this is 1/3, this is 1/3, and this is 1/3, because this is 1. Again, all of this changes when you go to intervals which are not of unit spacing, right? So be very careful there. But to illustrate and explain the basic concepts, I just want to do this in class, okay? The rest is in the books anyway. Anyway, everything that I say is in the books. All right, so this is where we are now. I was saying this is really all that we need to understand, because once we understand this, we can go from the 1D setting to the 2D setting, and from the 2D setting to the 4D setting. Good.
If for every slope we need f I minus 1 and f I plus 1, so
yes, he's good.
How can we?
He's good, right?
The first and the last one.
Make the world round.
Okay.
Make it cyclic or periodic, right? Then 0 equals n. Make it a bend. But you shouldn't accept that, because not everything is periodic or cyclic. All right, so don't copy this. This is just going to his question, because he answered that. And you have to solve it in your assignment, of course, or you have to deal with it. Don't copy it, just listen, because this is his idea now. Right? You have to tell me how you do it. I don't know how to do it. You pose the question, but posing a good question is already at least 50% of the answer, right? If you see the right question and you ask the right questions in life and in mathematics or computer science, then you already see the answer at the end of the tunnel, sometimes. So, all right, so he says, well, I'm starting here, Bernd, which is 0, and here is Mr. N, and then I have a bunch of things in between. Okay, for the in-between guys, no problem. It's always, for this, it is right minus left divided by 2, get the slope, right? For this guy, it is right minus left divided by 2, get the slope, right? You get a nice cubic curve. Right minus left, get something like this. Okay, fine. But now what do I do here? There is nothing here. There's nothing to the left. And for this guy, there is nothing to the right. So what do I do? What is a reasonable way to begin? This is my first stick. What would be a normal choice to choose as the initial slope? Like this? Maybe going in the direction of the second point, right? So why don't you just choose this direction as a slope direction? Huh? Right minus leftmost point divided by 1 in this case, right? So the G0 could be, I'm just saying this, there are many ways to do it, it's just F1 minus F0 divided by 1 because the spacing is 1, right? Same here. So the slope here, this guy, could be just the height of this guy minus this divided by 1, right? That's it. Is this good? Are there better ways? There are other ways to do it, right? The other way to assume is that the thing is periodic and cyclic, that everything is modulo n, and then you can, then n plus 1, you come back, n is 0, right? Huh? 0, 1, 2, 3, 4, 5, 6, 7, n, but n equals 0, and then you can, the right neighbor here would be this guy, right? If you do it, that's another way. But then actually that makes sense only if the phenomenon that you model is really periodic. So this becomes more complicated when you actually have a block, because you have different types of boundaries, right? Here you only have one type of boundary, the first and the last point. When you have a block, then you have different types of boundaries, right? The block has 8 corners, which is some type of boundary. The block has 12 edges, right, which is a different type of boundary. And the block has 6 faces, right, which is yet another type of boundary. And you have to worry about the points on all these boundaries, how to handle them. All the other happy points lying in the interior doesn't matter, right? But the points being a corner point, being an edge point, or being a face point requires some kind of treatment. Anyway, that's detail, right? You can figure it out. All right. So now we go to the 2D case. And I can do the 2D case very quickly because it is just the intermediary step to getting to the 3D case quickly. Now 2D. Case. I can still draw that somewhat. So we have one way to represent data, piecewise bilinear, right? Piecewise bilinear representation. And then what we want is a better representation, a piecewise bicubic. Piecewise bicubic representation. Bicubic rep for representation. All right, so how many should I draw? Maybe I'll just draw a few. So like this. Okay. Okay, I have 4 little happy cells lying down here in the xy plane, and my function value is going up. This is my mesh. And again, I use integer coordinates, 0, 1, 2 for the x direction, 0, 1, 2 for y, Cartesian. And then I have function values sticking out above the plane, looking like this. Zup, zup, and zup. And this is all I have. And then if I interpolate this stuff, this data, using a piecewise bilinear approach, then the resulting function or surface would look like this. Well, it connects everything with just lines, right? Linear. It is connecting things linearly in the x direction, and it's connecting things piecewise linearly in the y direction. Tuck, 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 tuck. Is this a beautiful surface or not? Is it nice? Depends, right? If your purpose calls for just this representation and it's good enough, then stop there. Don't make it more complicated. Right? But you have to know that all these patches have families of lines in them. Okay, not more. They cannot be curved. It's always 2 families of straight lines. That's why it's called the bilinear, linear plus linear, bilinear patch. And so obviously there is a discontinuity here at the boundary, right? You will see these discontinuities in the normal when you apply a lighting model to this. You will see that. It's not a smooth surface. So that's why we don't like it. Okay? So we want something like this, piecewise bicubic. In the piecewise bicubic case, the surface that we would get for the same type of data, stick, stick, and stick, high, lower, lowest, high, low, higher. Okay, for this data, again, x, y, f going up. Would be continuous in the slope. So there will be a curve like that. For that row of function values, there will be a curve like that. For that row of function values, there will be a curve like that. Okay, and now these curves are smooth at the breakpoints. Here, these curves are not smooth. There's a discontinuity, right? This slope abruptly changes to that. There's no way to smooth that away in the imaging result. You always will see that. But here you don't have that. Here you have smooth curves in x and y direction. And so this is the network of curves implied by that. And now, well, you can also see when you will draw for rendering more curves, then the whole patch actually looks like this. And it's really nice and smooth. Particularly, it will be smooth across this boundary. Right? The normal will not jump. So when you do an illumination, you won't see a line there. That's why we do that. So this is not so good, maybe. Okay. And this is maybe much better, right? Okay, here's a standing up there. Okay. All right, so now we only need to apply, only need to use this set of formulas for the 2D setting to get the polynomial coefficients for one of those bicubic patches. So I have to talk about the bicubic patch a little bit. So the building block. We only need to understand the building block. What is the building block? The building block is this thing. This piece is a bicubic patch. And I have to give you the definition in its Bernstein-Bezier form, and I have to tell you how to compute the coefficients for it. This is one building block. Building block and again, each of these patches is the same and requires the same computing machinery. You only need to write a procedure or module that does it for one, and then you call it over and over again, and you can do it in parallel, right, in a trivial way. Building block is the so-called bicubic patch, okay, or polynomial. So now I have to give you the definition of that guy. The bicubic polynomial in Bernstein-Bezier form Bezier representation so the analog to the stuff on the board over there is the two-dimensional generalization, so I try to sketch it. Sketch. All right, let's see whether I can sketch. Okay, all right. So now all of this lives in x, y, and a function space, f going up. And so here we have these control points of this patch, circles. And these control points have names. So now they have two indices. The first guy is called B0, 0, 0. This guy would be called B 3, 0. This guy would be called B 0, 3. And this guy would be B 3, 3. So then this guy, for example, would be B 1, 0. This would be B 2, 0, and so forth. You get the idea. This one is B 0, 1. This is B 0, 2. And I don't have to give the names of the others. The underlying patch or polynomial surface looks like this. Here's a curve. Here's a curve. Here's a curve. And here's a curve. Okay, those are the boundary curves of this patch that lies underneath this tent. You can think of this polygonal mesh as an envelope, an umbrella of the smooth cubic patch lying underneath. So the real surface that is implied by that tent of control polygons looks like this. If I sketch a few more curves on it, then you see how all of that relates. So there's this polygonal mesh. It's called a control net or control mesh. And then underneath lies this highly evaluated, highly resolved surface. So what is this surface? So this surface is a function f of xy, right? As I say, it's x, y, f depends on that. And so the coefficients in the expression will be these bij things times Bernstein polynomials. So that will be some kind of double sum now. Sum I from 0 to 3, j from 0 to 3. And now the coefficients are called bi, j times bi3 of x times bj 3 of y. Okay. Nothing has changed except it has become a double sum, but all the elements in there are the same. So these polynomials are defined just as the polynomials are defined over there. How do we use this building block to actually construct the overall smooth surface? What are we given and what do we need? Well, we are initially just given the sticks, and from the sticks we want to compute the smooth surfaces. So what is it that is still missing? We have the sticks, but what else do we need? Gradients. We don't have gradients, right? In order to take full advantage of that machinery, we need the sticks, but also we need to prescribe somehow meaningful tangent planes, slopes, gradients, right? And the way I've drawn it, you already know, at this point, you need two directional derivatives. You need the derivative in this direction to get this curve, and you need the directional derivative there to get this curve, right? That's the gradient. The gradient has two components now, derivative in x and derivative in y. All right. So now we need to worry about estimating these derivatives. Then we have everything that we need to actually compute these bij coefficients. So that's the next part. What next? What's needed? Well, we need good gradient estimates. Well, we need good gradient estimates. Gradients. Okay. All right, how should I sketch this? Well, do it like this. Here is my Cartesian grid. Okay. And so here is 0, I minus 1, I plus 1. Then this might be m. This is 0, 1, j. No, this would be j minus 1. This would be j plus 1. And the last one here might be n. So this is xy direction, and this is the function direction f. And what I need is I need a derivative for this point. Okay. How do I get the two derivatives at this point? I probably can compute it just based on local information. This case here resembles the case we had before. This is just the x case. Point in the middle, left neighbor, right? That's x direction. So the slope in x direction is given by, this is 1 and 1, right? This height of the right neighbor minus height of the left neighbor divided by 2 gives me the derivative in x. Okay. So the gradient at location xi yj equals I, j. Right, this location is just location ij there. Has two components. Is the gradient at location ij, I, j, and it has an x component, and it's a gradient at location ij, and it has a y component. Right? I need the derivative in x and the derivative in y. And as I said, we can just trust our eyes. Our eyes see this parabola, and this is the derivative for x. Okay. Where, and now I spell this out, what I did there in the illustration, where gradient ijx is, well, I did the same as I did in the 1D case, right minus left divided by 2. Okay, so then I have to give names to these sticks. So this here would be fi minus 1j. This would be fi plus 1j, right? So, and the difference, these guys, and divide by 2, it's 1/2 of fi plus 1j minus fi minus 1j. That's the first component of that gradient. Second component, I would consider, no, not that guy. I would consider this neighbor. And this neighbor, say. Again, my eye sees this behavior there. And then my eye differentiate this to get that slope. And so then this height is fi j plus 1. And this height is fi j minus 1. So then the gij y component of the gradient would be 1/2 of the neighbor in the back minus the neighbor in the front, fi j plus 1 minus fi j minus 1. Okay. Okay, now I have that. Okay. I still don't have the definition of the cubic patches over each of these little cells. That's the next step, right? Now I have function values and I have two derivatives at each point. Now the next step is the definition of each of these smooth cubic patches over each little square. All right. So from this, I want to get the coefficients. Now what can I do? Now I can determine the bij values from the f's and the g's. Can determine the bij values, the coefficients from the Fij and the gradients Gij x, gij y data. How should I show this? Maybe it's a building block again. The building block at this point looks like this. Building block is just understanding the configuration over one single square. So, and without losing any generality, I can just say this is 1, this is 0, this is y direction, this is 1, this is 0. And at this point, I have the 4 corner values and at each of these values I also have a slope, 2 slopes, one slope in x, one slope in y. Okay, so if I draw this like this, then the slopes that I used here to draw that were these 2 slopes in x. If I draw this guy like that, then the slopes that I have estimated somehow were these guys, were these slopes. And now I have to do this in the transversal direction, say this curve. So the slopes obviously I used for this were this slope and this slope. And I have also magically computed or estimated slopes for this. And then the slopes I used for that was this slope and this slope. Okay. This is just one cubic patch that somehow looks like this. Okay. And what do I need for this guy? I need the control coefficients. Needed is the control mesh, control net or control mesh. And so that is this particular mesh that I had on the board before. And there are 16 points. In the 1D case, I had 4. In the 2D case, I have 4 times 4, 16. In the 3D case, I will have 4 times 4 times 4, 64. In the 4D case, I will have many more. So this is the point B00. 0. This is the point B10. This is the point B20. This is the point B33. This would be the point B30. This guy, for example, would be the point B32. This guy here would be B11. This is B01. This guy would be, for example, B03, and so forth. And now we can think more abstractly and think in terms of the program that we have to write and have to understand the pattern, right? Once we understand the geometry and can sketch it for 1D and sketch it to some degree for 2D, then come the abstractions, then actually comes the pseudocode and the data structures and the indices, right, where you always make a mistake. So we all make a mistake there. I make a mistake there too. So let's see. Now we have to look at the formulas, how we get the bij's from the gradients and the f function values. Okay. Relationship between between Bij values and prescribed Fij and gradient data Gij x, Gij y data. And now just follow your intuition, okay? You have to oftentimes just trust your intuition and trust your gut feeling, okay? And then afterwards you can show that it's correct. Let's do this together, okay? Let's do this together and trust our intuition. All right. So here is the first point. Here is this polygon, right? Somewhere I have this polygon here. There's a thing here is the first point. Here is some second point. And somewhere there's a third point right here. I only have to understand what's happening in this corner, because if I understand again what happens in one corner, the other corners will have the same. So even within a building block, you only need to understand what happens at one corner, right? The stuff that happens at the other corners is the same. So here is B00, here is B01, here is B10, and this point here is B11. We need to understand only how to compute these four guys. If we know that, we can compute these four, those four, and the four in the upper left. That makes the whole 16, right? So what is B00? What is B10? Sometimes I make the comma, sometimes I don't, but I hope I don't confuse you. B01 and B11. Okay. So these slopes here indicate something. So the height of the stick was the value there, right? Function value f00. And the slopes here stand for something. So this slope is the slope G00 in x. And this slope here, the other slope, was the slope G00 in y direction, right? One slope here, one slope there. What do I need to compute? I need to compute the four circles which go into the Bernstein-Bezier expression. What are they? Help me, and just trust your instinct. B00 equals, it's a simple one.
F00.
Equals the value there, the function value f00, right? Now look at your formula from the 1D case. The first Bezier point, B1, was simply, what was it? It was the function value plus 1/3 times the derivative, right? Okay, so this one is function value 0 plus 1/3 times the derivative in x. And what do we call that? We call that the gradient in x direction at location 0. Okay, so what is B01? That's the same principle, now just done in y direction. That is function value f00 plus 1/3 going in, well, the direction of the gradient in y. Gradient in y direction at location 0. And the only new one, in a sense, is this guy, B11. Okay. Okay. In order to get from here to here, what do? We start here and move 1/3 unit in this direction of x. And then in order to get there, what do we need to do? We need to do this, what we already did there. So it's the concatenation going 1/3 of gx plus going 1/3 gy. So formalizing that, it's just f00 plus going 1/3 in gradient x direction, gx at 0 plus 1/3 going in gradient y direction at location 0. Okay. Now, another way to depict it is in a more abstract way. Okay, let's become a little bit more abstract. It's all the same, more abstract. More abstract. I just have my data structure. It's an array, right? A 2D array of stuff. Right? Here are the corners. This is the building block. This is the one building block. And I computed 16 points there, right? I can think of these 16 points like this, right? There are 16 points, these 16 circles, whatever I call them in my program. And I just told you how to compute the ones in the lower left corner. Now I trust that you probably can also follow your intuition and come up with the formulas for those four, and for those four. Just to be funny, we will do these four together, okay? And the other four you can do at home. Okay, so this would be F00, which was B00. And this point here is point F10. This point is F1, 1. This point is F0, 1. So then this is equal to B33. This guy here, this circle is B32. This guy here is B23. And this guy is B22. And I just write down the formula, so we do it together, the 4. Okay? Again, you just have to use your intuition and use the same apparatus over there, just with changing signs maybe, okay? Let's do this together. Okay. B33 equals what? Tell me. It's the function value there at the upper right corner. It's the function value there. Now let's do, which one next? Let's do this one, okay? B2, 3 is, what is that? Follow your intuition. It's a function value there, plus or minus something. You go left, it's the minus direction. So it's a function value there. Just trust your intuition. Okay, minus 1/3. The 1/3 is the magic 1/3 thing. Yes, minus 1/3 of something, of a gradient, right? Of a gradient. In which direction are we going? In x. So it's a gradient in x. Which direction are we talking about? The gradient that we have there, which was called G11 in our indexing. Okay. Okay, that's that. Minus. Now let's do this guy. B3, 2 equals F11 minus, again, 1/3 of the gradient, but this time the gradient in y direction at that upper right corner, 1, 1. And now this is the only tricky guy. Is it tricky? No, not really. It's just the same pattern. And then you have B22 equals the upper right value, F11. And it's minus 1/3 in x of that gradient, minus 1/3 in y of that gradient in y. Minus 1/3 gradient in x at that location, 1, 1, minus 1/3 of gradient in y at 1, 1. Okay? And the other four corners follow similarly by just playing the proper game with the alternating sign. Okay? Minus, plus, plus, minus. Okay? Now, I will not write down the 64 coefficients for the volume. Anyway, you don't really need these formulas. If you play the games properly as an elegant programmer, then you will recognize that this is all symmetric. You don't need the special case treatment. You can just change the indexing. You just turn this thing around, you rotate it by 90 degrees, and you call this point up there point 0, 0. Right? This is 0, 0, 1, 0, 0, 1, 1, 1. It's symmetric. You can view every corner as if it was corner 0, 0, and then you have the same module all over the place, right? It's another way. Either you do it for the different indices where you can only make mistakes because the mistake is hidden here in this plus-minus thing, right? You make a little bug there. But in order to avoid the bug, you always treat a corner as a corner in its own right, right? a corner, it has two neighbors and one guy diagonally opposed, and that's the same then everywhere. So you can reduce the number of errors you make. Anyway. All right, now comes the 3D case, and I won't be able to finish that, so I will just start it and then try to close the loop, coming back to why I'll be doing this in the context of raycasting. The 3D case. The 3D slash trivariate, right? Trivariate. Oops. Case. And no longer can I make these drawings because the function value now lives in the fourth dimension. And I can't do that. So all I can do is I can show the data cube. The data cube itself now is, or the building block. The building block is now a Bernstein-Bezier polynomial that lives over one cube. This is just one voxel element, and it will have 64 coefficients. Oops. Okay, and I will only sketch the coefficients on the side faces because otherwise it becomes just completely overcrowded. Okay, this is just one building block, and so these are the circles now. These circles are 64 in number. So these are the circles, the Bezier points, or the Bezier ordinates, on the front face, and there's a bunch on the top face, and there's a bunch on the side face to the right. I will name some of them so you get an intuition for the numbering and the indexing. This lower left bottom one would then be point B 0, 0, 0. This guy would be, for example, B 3, 0, 0. Another guy, this guy would be B 0, 0, 3. Upper top right would be the highest indexed one, B 3, 3, 3. This guy would be B 3, 3, 0, and so forth. So you get the feeling for that, right? So this is one building block. And the building block is now a trivariate function. F of x, y, z is a triple sum I from 0 to 3, j from 0 to 3, k from 0 to 3 of Bernstein coefficients bi, j, k times polynomials b I 3 of x times b j 3 of y times b k 3 of z. Okay. And so there will be 64 coefficients, 64 coefficients. And I'll talk more about that next time. But now I want to close the loop, coming back to what we do with this building block once we have it. Once we have this building block, we can use it for better ray casting. And that's what the goal was to begin with. We have now one of those building blocks living here. This is just one voxel of a voxel of 256 times 256 times 256 voxels, right? That you enter the data set. And you shoot one particular ray into this mesh, and sooner or later, this ray will also penetrate this particular volume element, this voxel. Okay? It will come from the left, happily, blah, 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 will enter, go through here, and then exit here. Okay, that's the ray. What do we have to do for rendering? We need to sample this guy, right, along the way. particularly, we need to sample it in the interior of each voxel that we are going through. So we have certain sample points. Okay. And what do we need to do? But at these 5 sample points, we need to compute 5 colors and 5 opacities. And so this thing is now f equals f of x, y, z, which is this particular beast over here. It is of this form, right? And now we evaluate that guy at these sample locations, 1, 2, 3, 4, 5. Evaluate that representation of the function, the field, the density, the MRI scan, the CAT scan, the PET scan, whatever it is, the flow field. Evaluate the expression at 5 sample points. And then you get 5 beautiful color I and opacity I, right? Values. Right? And here, in your pixel plane, you get a very nice pixel when you do this for all voxels. Okay. 5? Oh, these are the sample. This is just an example. I just chose it to be 5. 5 is a good number, right? I like 5. Just using one sample in this high polynomial thing might not be good enough. Using 2 might not be good enough. 5 is good. Somewhere between 5 and 10 would be okay for a cubic polynomial. That's okay. How many points do you need to use for sampling? What is enough? What is not enough? Do some research on that one as well, right? There's a relationship between the spacing, the resolution of your mesh, the polynomial that you use, and the number of samples you should be using within each cell to get all the detail and not to miss anything. And at the same time, you want to produce a picture in the smallest amount of time possible, right? Real time. So what is the right balance there? So you can think about that. I see you on Thursday night. Bye-bye.